Okay, so hi everyone. Welcome to the 58th session of the MedAI group exchange sessions. So this week we have Natalie from Stanford here with us to speak about her work on fairness in representation learning. So Natalie is an incoming PhD student at Stanford University, and she recently received her master's from the University of Toronto. She previously graduated with a bachelor's degree in mathematics from the University of Southern California with a minors in computer science and chemistry. And her research largely focuses on machine learning through differential privacy, algorithmic fairness, and applications to clinical and biological settings. So thanks so much, Natalie, for joining us today. And before we start, do you have any preferences on how you'd like to take questions? Would you like them at the end, or are you okay with us interrupting in between?
I think at the end would be easier if that's okay, but whatever works, yeah.
Okay, sounds good. Yeah. So without further ado, let me hand it over to Natalie.
So yeah, thanks so much, Nanda. And so yeah, as Nanda said, my name is Natalie Dullerud, and I'm starting as a computer science PhD student this quarter at Stanford. And today I'm going to be giving a talk on a recent paper I published at ICLR 2022 with my listed collaborators here. On fairness in deep metric learning. And in particular, I'll be discussing evaluation and mitigation of bias in the context of deep metric learning. And so here's an overview of the sort of talk components. And first, I'll be reviewing sort of a background in deep metric learning, classical fairness in sort of classification settings, and previous fairness literature on fairness and representation learning at large. So to quickly sort of recap standard methods in deep metric learning basically extends standard metric learning to deep neural networks. So the goal is to learn a similarity metric over data that represents actual semantic similarities. So that's really similar to standard metric learning. But the idea in deep metric learning is that the similarity metric is parameterized by the composition of the Euclidean distance with a deep neural network embedding. And so basically giving a data set with a set of features and labels, the deep neural network embedding ideally embeds samples of the same target class close to each other and samples of differing target classes like far away from each other. And so then the embeddings are typically normalized to lie on the unit hypersphere, which is shown in the infographic here. And sort of the objectives that we use to learn these types of metric spaces will range from, contrastive sort of ranking-based training, which uses tuples of data, like pairwise, triplet, or sort of higher order tuple-based training, procedures that bring down the sort of effective complexity of the tuple space, or sort of introducing learnable tuple constituents. And so in the simple case, the tuples usually consist of an anchor sample, a positive sample, which is a sample that's the same class as the anchor sample, and a negative sample, which is a sample of a distinct class or differing class from the anchor sample. Or you have some extension of this tuple structure, you have multiple negatives or multiple positive samples. And so the objective essentially penalizes positive samples that embed far from the anchor samples and negative samples that embed close to the anchor sample in sort of a sort of simple way. And so then when this is propagated back through the network, the loss essentially pushes positive pairs closer together and negative pairs farther apart. And so here I just showed it sort of with bird species, but you can think about this for a variety of settings. And so another sort of important component of deep metric learning that I won't review that extensively, but is really important, is the mining procedure. And we think about like batch sampling, this is batch mining. And so when you have a batch, you need essentially tuples, as I just described, anchor, positive, negative. And so this is basically, this mining procedure is done in order to choose sets of tuples over the very, very large tuple space that will actually improve the network, instead of just randomly selecting them from all possible tuples. And so owing to the fact that deep metric learning models similarities over the data as opposed to sort of explicit class boundaries, deep metric learning is really favored for tasks like zero-shot or few-shot retrieval, facial recognition, and ultimately the sort of representations that we build lend very easily to doing simple linear or clustering classifiers downstream. And so now that I've sort of covered a little bit on deep metric learning, I'll sort of move on to another component of the research, which is algorithmic fairness. And probably most of the audience are familiar to some extent with fairness, but I'll just briefly talk about concepts in fairness classification and then jump into fairness and representation learning. So there is the concept of individual fairness, but I'll really mostly be talking about group or subgroup fairness, which essentially is fairness with respect to some protected attribute like race or gender identity, age, etc. And so some of the core questions in the sort of canon of fairness literature in machine learning are sort of what causes bias propagated by machine learning models, and how do we sort of quantify the bias of machine learning models? And in terms of sources of bias, causes of bias, there have been a number of papers that sort of discuss this, but for the most part, bias in machine learning models arises naturally from social bias in data and sort of lack of mitigation of that bias in the algorithms we use. And so the social bias in data can include a lot of different things. There are many sources of bias in data: imbalance, noise, entangled or interrelated features in data collection, or in most cases, it's some combination of these. And so most algorithms that aim to improve fairness in ML models have sort of focused on alleviating the bias in the algorithm from these sources of bias in the data. And so the next question is sort of how to quantify fairness or bias in an algorithm. And so here there have been some landmark papers that have largely drawn from sort of sociological ideals of fairness, and sort of classical fairness definitions can mostly be categorized to some extent into these three categories. So anti-classification essentially stipulates that an algorithm does not use protected attribute information to make decisions or predictions, nor does it use proxy features for protected attribute information. Parity essentially defines fairness as sort of equal distribution of classification errors or classification performance measured by some metric across the defined subgroups. And then sort of similarly, calibration describes fairness as independence between the model outcome and the protected attribute conditioned on some risk score, which might be, for example, the sort of ground truth label or something like that. So in most recent fairness literature, researchers mostly seem to look at parity and calibration due to sort of the difficulty of completely eliminating any proxy features for protected attribute information in sort of the anti-classification paradigm. And, the fact that ultimately ignoring sort of protected attribute information can sort of cause some harm towards, minoritized groups. And so nonetheless, there are differing notions of fairness and they can be useful in different domains. So there is sort of a benefit to having multiple notions of fairness. And typically the actual quantification of sort of the two latter metrics are performance gaps in classification. So for example, if we're concerned about parity with respect to accuracy, we could look at the sort of difference in average accuracy between subgroups. These subgroups are partitioned by the protected attribute. And so this is largely what we'll follow in our work. I do want to sort of make a note, because it is worth mentioning, that there are sort of more recent conceptualizations of fairness or repairing bias. And the ones that I list here are definitely not exhaustive, but these sort of challenge classical notions of fairness in machine learning literature. So the ones I listed here are worst group utility, so essentially maximizing the utility or performance of the worst performing group, and algorithmic equity, which is more complex and sort of accounts for bias, human bias in a variety of ways. And you can sort of imagine that, for instance, worst group utility might be well suited for something like medicine, where, all subgroups would probably prefer a model that gets their diagnosis right at sort of the maximal amount of time, as opposed to a model that, performs sort of okay on average, but has a really small subgroup gap. And nonetheless, our research, will focus mostly on measuring bias via subgroup gaps, just because of the domains we examine sort of support this, and we'll sort of get more into that later. So now I've talked a little bit about fairness and classification. We can sort of move on to fairness and representation learning. So demetric learning exists sort of as a subset of representation learning. And fairness in representation learning has largely been characterized by downstream classification fairness. So the goal here with sort of fairness in representation learning has generally been to learn a fair mapping from an original domain to a latent domain, so that classifiers trained on these representations lie in the latent domain, are more likely to be agnostic to the sensitive attribute or have low subgroup gaps in sort of downstream tasks. So basically, we train a representation learning model and assess its fairness via downstream applications. For example, training a logistic regressor or some sort of simple linear classifier on our representations, and then use one of these sort of aforementioned fairness definitions to quantify the bias of the representation learning model. So while there is, some study of fairness and transfer learning, and that's been explored in the representation learning literature, sort of the measures of bias are still predominantly in sort of downstream classification as a sort of avenue to measure fairness of the representation learning algorithm or model. But there are kind of quite a few disadvantages to sort of measuring or understanding fairness of a representation learning method via sort of downstream classification. And I kind of only will touch on a couple here that are sort of relevant to us, but the sort of primary reasons that this approach to sort of realizing the fairness of a representation learning model via downstream classification is sort of flawed is in some scenarios, it sort of ignores the effect of even simple downstream classification algorithms on the measured fairness, which is not really related to the fairness of the representation learning model itself, which is ultimately really what we're trying to test. And there's a couple other things that sort of study sort of the relationship between downstream classification fairness and upstream sort of representation learning fairness. There was sort of a paper published recently on basically the ability to sort of adversarially manipulate the data downstream in order to always produce a biased model downstream, regardless of the upstream embedding fairness. And even if you use, the same data set downstream as you use upstream, there's still sort of a dissonance because you are sort of adding an additional component, which is kind of hard to control. And so this obviously, presents sort of an issue with how we measure the fairness of representation learning models, and is especially pertinent for demetric learning, where one of the main use cases is zero-shot learning. So we need to ensure that any downstream application of the embedding is fair. And so sort of various previous methods have nonetheless looked at sort of fair feature extraction, feature learning, and representation learning to the end of downstream classification fairness. And I've only listed a couple of categories here of sort of proposed fairness improvements. But most literature focuses on sort of variational inference, disentanglement, or potentially adversarial learning motivated approaches, just in order to achieve fairness in representation learning. But again, this is tested via downstream classification. So in these settings, literature has sort of focused on optimizing approximations of mutual information between representations and sensitive attributes. Okay. So why does this not work quite as well in demetric learning? So as I was saying earlier, sort of the primary applications of demetric learning encompass, zero-shot generalization, facial recognition, and retrieval, which is, often sort of a direct use of zero-shot generalization, and it sort of clearly has fairness implications. Now, like I said, there's been a lot of sort of exploration of transfer learning, but again, a lot of this has been sort of empirical, and it's sort of obviously untenable to sort of test all possible downstream applications of a certain representation. And so there's some sort of abusive language in the generalization literature, but in this context, I mean, when I say zero-shot generalization, I sort of am referring to the problem in which you have a training task and a test task that differ in feature and or label distribution completely. So at test time, the machine learning model will need to immediately adapt to the new task and perform adequately on sort of newly introduced test distribution. So this sort of differs from few-shot learning, which demetric learning is also used for, where the model is allowed to be learned for a couple of steps on the test distribution. So for example, I just had a little example here. So basically in the vision domain, a model might be trained on images of zebra and polar bears and must be able to sort of differentiate them as such. And then at test time, the model is asked to sort of distinguish between otters and tigers and should perform, similarly well. And we can think that, humans do this, like even if you've never seen an animal before, if you've seen multiple images of that animal, if it's different sort of enough, you could be able to sort of understand that that's one type of animal, and it's a different animal than the ones that you've seen before. And so, deep metric learning is pretty well suited for this problem because the goal is to learn semantic similarities as opposed to, a classification system. So for that reason, the model should be able to sort of learn similarities between new sets of images and distinguish between images of, for example, different species without ever seeing those species before. And so in the case of facial recognition and retrieval, basically being able to distinguish and identify new faces comes sort of with its own host of fairness issues, like the ability to distinguish individuals with similar skin tones or of the same gender identity, et cetera. And there's been kind of quite a bit of talk about sort of fairness issues in the context of facial recognition. But since we don't know the test distribution at train time, we sort of need to be able to define and understand fairness in the embedding space itself, not necessarily in sort of a downstream classification setting. So this leads kind of nicely into our work. And so our work focuses sort of on three core tenets: developing a framework for understanding fairness and quantifying fairness in the representation space of deep metric learning, where we sort of draw on previous notions of performance and generalization in the representation space, and then validating our definitions via downstream classification and sort of understanding the effect of bias in the representation space on downstream classification, and finally, sort of proposing an initial solution to mitigating bias in the representation space of deep metric learning, which leverages sort of previous deep metric learning literature to produce sort of a DML-specific fairness boosting method. So first, we'll talk about how to define fairness in deep metric learning and what we use and sort of what we're proposing. So to define fairness in DML spaces, we follow sort of previous classification literature, which understands fairness as subpopulation gaps over standard performance metrics, but we adapt sort of these previous ideas for deep metric learning. And so we construct three fairness definitions that correspond to sort of three salient aspects of the embedding space: local sample structure, global sample structure, and feature space characterization. So essentially, we understand local structure through the similarities between a point and its key nearest neighbors. And this essentially corresponds to a standard performance metric in deep metric learning, which is recall at k. And recall at k measures sort of the pseudo classification of a data point at a local level. So basically, in other words, we average the binary variable of whether or not each data point has a data point in its k nearest neighbors of the same class over the data set as a sort of accuracy measure. And obviously, the magnitude of the locality depends on the choice of k. And this definition is sort of partially inspired by this most common metric in deep metric learning, but also sort of aligns with conceptualizations of fairness and classification, in that, a model outcome should be independent of inclusion in a particular subpopulation. So we basically desire that the probability that there exists a sample of the same class in a given data point's k nearest neighbors is equal across all subpopulations. So that's defined here. And the way that we sort of empirically quantify this is we compute the sort of performance gap according to recall at k across subgroups. And so next, we formulate global sample structure as the pairwise distances between positive and negative pairs, and desire that essentially the expectation over these distances is the same over all subpopulations. And so this corresponds sort of variously with alignment and normalized mutual information measures in DML. And alignment really succinctly captures the similarity structure learned by the representations with respect to the target labels through measuring distances between pairs of samples. And so as these pairs of samples extend across the embedding space, we use this to sort of signalize global sample structure. And here you can kind of see what this looks like on the embedded hypersphere. And so we sort of leverage this concept of alignment to construct our second fairness definition, which stipulates that the expectation over pairwise distances between positive pairs and negative pairs respectively be equal over subpopulations. And so, a potentially stronger version of this would be that we require that the distribution of distances itself not just the expectation be the same, but this would be kind of difficult to measure and also potentially too sort of strong to satisfy empirically. So we instead use expectation. And so to measure this, we can basically look at the empirical means of these values and then look at sort of the gaps between subgroups. And so finally, we turn to sort of a more abstract definition, which is feature space characterization. And so previous works have shown that various concepts of uniformity over the hypersphere embedding are highly correlated with generalization performance, and it characterizes the feature space really nicely. So as I stated earlier, sort of an important contribution of the work is understanding the feature space or representation space itself outside of class-specific definitions of fairness, which we largely already cover with the first two definitions, and sort of relate more directly to a sort of specific downstream classification fairness. But uniformity is, a bit more nebulous as a concept, and there isn't really a general consensus on the way to best measure this, or even sort of what uniformity explicitly means. And there are multiple sort of definitions, as I said, to measure uniformity, both in terms of the uniformity of the features themselves and the uniformity of the distribution over samples over sort of the unit hypersphere. And so in terms of the latter, we might measure the extent to which the distribution of samples over the representation space conforms to uniformity via the expectation of the Gaussian potential function or the radial basis function that's shown sort of on the bottom left over pairs of embedded samples. And in terms of sort of measuring the uniformity over the features themselves that we've learned, we could maybe approximate the singular values of the embedding space using the embedded data set, and then compare those singular values to the uniform distribution via some divergence measure. Here we use Kale divergence. And so we use the sort of latter method for defining uniformity when we're actually doing in our empirical studies, but in sort of our definition, we leave it sort of general. So ultimately, we desire that the uniformity over all subpopulations is equally good. And so essentially that the sort of distribution of samples over parts of the hypersphere are equally conformed to uniformity over all subpopulations. And again, we leave sort of the definition of uniformity open. And so now that we've sort of constructed these definitions, we want to both be able to validate them, but also return to sort of the dissonance between upstream fairness and downstream fairness. So in other words, basically the fairness measured or sort of incurred in the upstream space and the fairness in the downstream space. And our primary questions were sort of how to understand the relationship between fairness in deep metric learning and the effect of these embeddings on downstream classification fairness. So we'll move on to that, and we'll sort of discuss some interesting results we had on this front. So first, I just wanted to talk about our experimental setup so that the empirical results are a bit more clear, but basically wanted to test sort of, as I said, that relationship between upstream and downstream bias. And so we wanted to test it in a case where we can modulate the amount of bias and experiment with the effects of the models involved, and also on data sets which are standardly used in deep metric learning benchmark papers. So for that reason, we used Cub 200, which is a data set of images of birds, and the labels are typically the species, and CARS 196, which is a data set of car images, and the labels basically correspond to make and model. Obviously, we don't have any intuitive fairness problem here, so we basically contrive imbalance in the data sets to create the problem so that we can explore a little bit more how much imbalance leads to how much imbalance downstream and stuff like this. And so basically the way that we contrive this is we randomly select 50 groups, reduce the number of images seen in these groups during training by 40%, and inflate the other groups in the training data set in order to make sure that we still have the same number of training data points when we train with the imbalanced data set as opposed to the original data set. And so for control, we also train on the original data set, which is balanced for comparison. And on the next slide, you'll see results basically where we take these two upstream models, one trained on the imbalanced data one trained on the balanced data and trained downstream classification models on both respectively, with the original balanced data set to basically try to ascertain to what extent bias propagates to downstream tasks. And so additionally, in later experiments, we also use labeled faces in the wild LFW and celeb A for facial recognition, taking race and skin tone respectively to be protected attributes. And this is sort of intended to be sort of a primary example of real world data with a task that has sort of documented fairness issues. And so as described in the last slide here, we compare subgroup gaps in downstream classification trained on deep metric learning embeddings that are trained with balanced data and imbalanced data. However, we have to note here that the downstream classification tasks are always trained on balanced data. So we can see here that the performance gaps in the upstream model differ significantly between the balanced upstream embedding and the imbalanced upstream embedding, as we would expect. And this, provides hopefully some validation for our definitions. But the sort of surprising component of this is that the bias propagates downstream, even though both downstream models are trained with real balanced data with respect to the chosen groups. So we conclude that, even in the best case scenario where you have access to a real balanced data set downstream, you can't actually overcome bias that was incurred in the representation space. And so, as I mentioned earlier, imbalance isn't the only source of bias in data sets, but in our case, we randomly select 50 groups on which to reduce the number of samples, and these are normally equal in the original training data set. So we don't really have any reason to believe that there's any other source of bias with respect to those groups in the data set except for our contrived imbalance. So this is really showing that even when we remove the source of bias downstream, we don't see an improvement in the gaps downstream due to the bias incurred in the upstream embedding. And this is pretty important because there's kind of been a move towards large entities, that have huge sieves of private data. They'll release embedding models trained on their own data for use by, smaller entities, which can maybe train a simple downstream model and get good accuracy on a smaller data set. We see this in language models, but we've also sort of seen this with other representation learning models as well. And sort of the issue with this framework, as we've shown, is that releasing sort of large embedding models for use in unknown downstream tasks is the downstream task user, even if they have balanced data, can't really overcome the bias that was potentially incurred in the embedding space, even in sort of the best case scenario. And so we turn basically to our next question, which is to what extent bias propagates. So in other words, if we contrive a less imbalance in the upstream embedding, can we sort of overcome that bias downstream by rebalancing the data set with real data? So here across the sort of x-axis, the numbers indicate the imbalance with respect to the minoritized and majoritized groups that we had contrived. And again, note that the imbalance here is only in the upstream embedding. In the downstream embedding, we still use the original balanced data set. We're trying to see if we have imbalanced data in the upstream embedding, how much does that propagate downstream, even if the downstream task has a balanced data set. And so even with sort of minimal bias, in the case of sort of a 40-60 split where the minoritized groups comprise 40% of the training samples, and the majoritized groups comprise 60%, the bias nonetheless propagates downstream, even though the downstream training data is not imbalanced. So obviously, mitigation of the bias here needs to sort of occur in the upstream embedding as opposed to the downstream classification task. Because we're unable to sort of overcome bias in downstream classification, even in the best case scenario, where we have real data that isn't oversampled, that removes the source of bias. So now I'll kind of offer sort of an initial solution to this problem in sort of the context of deep metric learning. And to motivate our method and sort of consider the intuition behind it, I'll chat just a little bit about our considerations. So a sort of initial solution that sort of has, I would say, dominated some of the fairness literature, a kind of naive solution is to basically oversample minoritized groups in order to improve the fairness outcomes. However, when we think about this in the context of zero-shot generalization, we run into sort of a bit of an issue, which is that we want the embedding space to generalize similarly across subgroups. And if we sort of oversample from one subgroup, we might sort of overfit to that on that subgroup. And that subgroup then might generalize more poorly to new test distributions of the same subgroup than to test classes of other subgroups. And that would kind of hurt fairness according to sort of our definitions. And additionally, sort of due to the mining procedure in deep metric learning, we should already be looking more at samples that are more difficult to semantically separate according to class. Our results, I showed a couple of them here, but you can see all of them in the paper. We looked at a combination of over 15 different sort of standard methods in deep metric learning and a variety of mining procedures. And we don't see any improvement in fairness across mining procedures. So for that reason, we sort of primarily draw from previous literature in deep metric learning, zero-shot generalization, and disentanglement literature in sort of a variety of representation learning domains to inform our idea. And finally, we sort of think about how we can optimize our fairness definitions. And so we want to try to sort of equalize metrics across subgroups, as we sort of discussed earlier. So now I'll sort of introduce an initial proposal for boosting fairness in deep metric learning spaces and discuss some of our results, both upstream and downstream. And so our proposed method basically consists of a couple components that work to improve the fairness of the model in line with sort of similarly motivated methods in disentanglement. So instead of learning a single metric space that encodes the similarities between samples according to the target labels, the model learns two distinct metric spaces off of the penultimate layer of the model. And so specifically, sort of these two representations will branch off from the deep metric embedding model at the sort of second to last layer. And these two representations encode similarity metrics learned over the sensitive attribute and the target label respectively. And so the sensitive attribute embedding layer will be discarded at test time, and the resulting network expresses a similarity metric with respect to the target class. And during training, we essentially will de-correlate that embedding with the embedding of the sensitive attribute so that the ultimate deployed model is an embedding of the target class, but decorrelated from the sensitive attribute embedding. And so the decorrelation occurs via adversarial separation, which is achieved according to basically a gradient reversal operation. And this is really a method from a sort of previous deep metric learning paper that was focused on diversifying the learned embedding via decorrelation among features for better zero-shot generalization. But in our context, we use it to decorrelate with the sensitive attribute. And so here we employ basically just a standard multi-layer perceptron, so MLP, to learn to decorrelate the embeddings, and we take steps on this MLP simultaneously with the DML model. And so we achieve the sort of multiple decorrelated last embedding layers that have learned a similarity metric for these two, target class and sensitive attribute respectively via this loss. And I'll break down the objective here into its components and how they sort of translate to the final product. So our loss term incorporates primarily three components. The first of which is the loss for the target label embedding. So here the loss function itself is left general. So any metric learning loss can be used, but the tuples are sampled from the distribution over target labels, and the loss only pertains to the embeddings in the target label embedding. So essentially the target label loss stays the same, but it's only calculated with respect to a single embedding off the penultimate layer of the model. And nonetheless, the gradient propagates back through the rest of the model. And then the second term is the loss for the sensitive attribute embedding. So here we're trying to learn similarities characterized over the subgroups, which seems sort of counterintuitive to some definitions of fairness. However, we then decorrelate this embedding with the target label embedding. So the target label embedding is decorrelated from information about the sensitive attribute. And the loss is essentially the same. So any loss function can be used, but most importantly, the tuples are sampled from the distribution over sensitive attributes as opposed to target class. So for example, instead of a triplet containing an anchor, a positive sample, and a negative sample with respect to target class, the triplet that's sampled will contain an anchor, a positive sample, where the sample has the same protected attribute value as the anchor, and a negative sample where the negative sample has a different protected attribute than the anchor. And so on the left here, you can sort of see the two distinct embeddings that are learned off the last layer of the model. On the top, you can see that the sensitive attribute embedding embeds bird images near each other if the images have birds with the same dominant color. And the target class embedding shows clusters according to the species of bird, which is the ultimate target label set. And so the idea here is that the ultimate target class should be decorrelated from the sensitive attribute, which here is taken to be bird color. So we just kind of illustrated that. Here you can see a yellow bird in the sort of sensitive attribute embedding. It's clearly embedded near other images of yellow birds. In the actual deployed model, we want to force the model with this loss to essentially be able to distinguish between different species of bird without relying on just the sensitive attribute. So here you can see that where this image of a yellow bird is clustered is sort of far away in the target embedding from other images of yellow birds. And so this is sort of ideally what we get, and it's still sort of nicely clustered. And so again, sort of the gradient from the sensitive attribute embedding is propagated back through the model. So the model, even when the sensitive attribute embedding is removed at test time, will still sort of retain information about the sensitive attribute depending on these constants, alpha SA and rho, which I'll return to in a couple of slides. And so finally, we have the component that learns the decorrelation. So in order to minimize the correlation between the target embedding and the sensitive attribute embedding, we use adversarial separation, which is intended to minimize the mutual information between pairs of embeddings. And so the task of essentially mutual information minimization is accomplished through learning an MLP to maximize the pair's correlation, which is C, and consequently performing a gradient reversal R, which will then, basically minimize the pair's correlation. So this inverts the gradients during backpropagation. And so the MLP psi here is trained to maximize C function. And so now to sort of discuss the constants, we have alpha SA, which essentially weights the sensitive attribute loss, and rho, which controls the magnitude of decorrelation. So since rho modulates the decorrelation term, the resulting model can retain some attribute information. And that's why we have the name partial decorrelation. Additionally, we can sort of control the extent to which the model up to the penultimate layer learns the sensitive attribute by weighting the sensitive attribute loss higher or lower. And so we keep these parameters constant in our sort of experiments through training, and we set them via hyperparameter search that maximizes sort of the resulting fairness of the model. But you could alternatively optimize them, according to a distinct objective, worst group utility, some other sort of concept of fairness that you like, or use, for example, decay, or you could learn the parameters while you're sort of training to optimize fairness. And this sort of final idea is pretty common in deep metric learning. A lot of the losses rely on sort of learning a certain, for example, margin or something like this. So as I said, we keep them constant in our training, and they were set via hyperparameter search, but there are other sort of ways that you could optimize these values. Okay, so to jump into our sort of results with Parade, we basically compare it against standard deep metric learning and naive baselines for fairness improvements. And we show that in our chosen data sets here, shown LFW, we have improved subgroup gaps under Parade across metrics. And pointing out here that LFW has a lot of singleton classes, so recall at 1 is not a super reliable metric just because there's potentially most data points that are singleton, that none of them can have a data point in their one nearest neighbor that's the same class as them, because they're the only image in their class. And so we mostly focus on sort of the other ones for this data set in particular, but we see that these improvements in subgroup gaps are also observed downstream in subgroup gaps over recall, precision, accuracy, and we use the ascribed race of individuals and labeled faces in the wild as the protected attribute and decorrelated our facial recognition system with race. And so the ultimate sort of parade model, geometric learning model, is able to correctly sort of distinguish between individuals of the same race and hopefully learn important similarities between individuals and amongst individuals that do not correspond to race characteristics. Sorry, there we go. So unfortunately in Celeb A, we don't observe the same trend when we look across all skin tones ascribed to individuals in Celeb A. So we hypothesize here that as we average equally over all subgroups when computing the gaps, parade is sort of hurt compared to naive baseline of sort of oversampling due to seeing fewer than 1% of the data set with skin tone 6, which is the darkest skin tone. So if we remove skin tone 6 from analysis, parade consistently improves over the naive baseline. But this is really still very impactful and harmful for skin tone 6. And so we note that sort of in cases where there's very severe imbalance, like in Celeb A skin tone, parade might not be sort of best suited. And so in these cases, we think that maybe, oversampling combined with parade might be a better approach. And so we additionally compared parade downstream with mitigation methods downstream, like domain-independent training and oversampling methods from previous classification literature. And we basically took the best performing methods for downstream classification and compare them to parade downstream. And we find that the mitigation of bias upstream via parade improves over basically existing methods of mitigation downstream. And so again, this kind of reinforces our point that fairness improvements and representation learning need to sort of occur in the representation space itself and not downstream, and also sort of bolsters parade. And so as stated before, there are like a few limitations of parade, and it sort of serves as sort of just an initial exploratory solution to fairness and deep metric learning. However, so I'll kind of discuss a couple of these limitations. So as with sort of other fairness with awareness methods, it requires protected attribute information to be available when using the method, which might be pretty unrealistic in some cases and often in sort of many cases. And so since parade uses sort of information on only predefined sensitive attributes, it might be unfair with respect to other sensitive attributes. As opposed to other fairness boosting methods, it does sort of have the advantage in addressing sort of a combinatorial number of protected attributes that intersect in sort of multi-attribute fairness, because it doesn't, the algorithm is not combinatorial in the number of sensitive attributes. So it'll scale, significantly sub-combinatorially. It doesn't add any overhead to include more attributes. And so as shown in sort of previous slides, it doesn't really do well in the cases of extreme imbalance, like in Celeb A, where a particular subgroup comprised less than 1% of the data set. And finally, the constants involved in the objective term are chosen by the user. And although there are ways proposed to optimize these, they will be, inevitably dependent on a certain data set or the data set used for hyperparameter training. So potentially that can be improved. So with that, I'll quickly move to future work. And so mostly we're interested in basically expanding our definitions and methods to improve deep metric learning according to the limitations I sort of just discussed. And specifically, as I mentioned earlier, we leave our definition relating to uniformity open in terms of the exact definition or measure of uniformity. And exploring novel measures of uniformity would lend more to our characterization of feature space for different subgroups. Also in our definition, we estimate sort of the uniformity over the subgroups separately, not really how the representation structure over particular subgroups contributes to the global uniformity, which might be more useful, as sort of uniformity over the entire hypersphere is more important to generalization. And so the difficulty in estimating sort of this contribution of different subgroups is how to measure the contribution of, a part of the representation space to the global sort of representation space. But sort of nonetheless, in sort of other words, we would like to make the switch from measuring local uniformity to local contribution to global uniformity. And so, as I mentioned in the limitation slides, it would be sort of ideal if we could both measure fairness without explicit demographic information and experiment with fairness boosting methods that do not require demographic information. And so this is kind of an open problem at the moment in the fairness space. And some recent work has pointed to the idea of computationally identifiable subgroups, which essentially hinges on the assumption that subgroups that are at risk in machine learning are computationally identifiable, largely via the loss landscape. And so maybe experimenting with this in the representation learning setting and specifically in deep metric learning would allow us to sort of optimize fairness with respect to any protected attribute as opposed to sort of predefined attributes. And sort of another line of potential further research would be probing fairness in the zero-shot learning setting a little bit more. We've started it here, looked at sort of generalizing to new classes of images of individuals in facial recognition, and also looking at it in sort of classic deep metric learning contexts like Cub 200, Cars 196, but we'd like to sort of continue it in as many other contexts as possible. Okay, so yeah, that's the end of my talk, and thanks so much for listening, and obviously feel free to ask questions or even reach out to me personally after the talk.
Awesome. Thanks so much, Natalie. So I guess we have the floor open for questions. And so I can actually get started with one. So it was interesting to me that you said like Parade basically requires usage of like you need to know information about the sensitive user attribute. So
Right.
I was thinking, is there some way you can extract these kind of sensitive attributes like in an unsupervised manner and then use Parade in conjunction with it? And do you have any suggestions of like how to explore this kind of like a two-step process?
Yeah, so there's a lot of like interesting unsupervised representation learning methods that might help. Sort of one thing that I had been thinking about, which I had kind of mentioned in the future work, was the idea of subgroups being computationally identifiable, that maybe there's some way that we can use, loss landscapes in unsupervised learning or something like this, that we can actually come up with, subgroups that are actually at risk for, having poorer performance with our models. And then we can use those subgroups that we found through some sort of other method, we don't have to be given that information to then sort of de-correlate. So yeah, I think that would be a super interesting sort of line of continued research. Yeah.
Awesome. And I guess before actually going into questions, I forgot to like say, let's all give a big round of applause for Natalie for the amazing talk.
Yeah.
So, yeah, open to more questions if people have.
Hey, Natalie,
Yeah,
it's a very interesting talk. I just want to ask you one quick question. Like sometimes actually the sensitive attributes is not possible to decorrelate with a target task,
Yes.
So because, for example, like imagine like particular age versus, I don't know, maybe like comorbidities or disease. Exactly as you give an example, particular species of a tiger versus like the color, sometimes it's not possible to decorrelate.
Yes.
What do you suggest on that kind of cases?
Right, so that's kind of the idea here. Let me go back on my slides a little bit. Behind these constants is that the decorrelation is only partial and you can still weight it a lot lower. So like, for example, let's say in the case of like breast cancer diagnosis, right? You might want some, for example, sex information to be still contained in your model because there might be certain risks for different groups. You can still modulate essentially this sort of parameter, this constant rho or the sort of alpha setting. So your model still does learn information about the sensitive attribute, because the sensitive attribute embedding is still branching off from the last layer of the model. But you can sort of modulate it based on sort of these constants. But I guess, as you're saying, perhaps in some cases, it sort of might be even more egregious. I think, like I was saying, maybe setting these as learnable parameters that sort of as you go, you're learning what these sort of constants should be that modulate the sort of decorrelation, and how much the model learns about the sensitive attribute is sort of potentially the best way to address that. I don't know if that answers your question, but
yeah, that answers. So another thing is like for this particular task, actually you are using like an addition of your sensitive attribute task loss with a modulation parameter, right? But why addition? Why you don't want to subtract it? Because you want to reduce that loss of the sensitive attributes, right? Like actually no, opposite. Like you want to like escalate the loss of the sensitive attribute, right? With the same CNN backbone. So why don't want to go in the opposite direction?
Right. So the decorrelation. So basically, you still have to learn the actual embedding that characterizes similarities over the sensitive attribute. So you still want to learn that. The decorrelation part, which is negative, as you can see, is the part that actually decorrelates those embeddings. So it removes information about the sensitive attribute from the target class embedding.
Right. But I think this only holds if you start training the convolution backbone from the scratch. If, for example, if you have a pre-training of a convolution backbone, whatever, ImagineNet or whatever pre-training, then it doesn't really hold, right? Because your model still actually already learned some of these attributes beforehand, before you start your decorrelation term.
Yeah, so if you have to train them basically simultaneously, yes.
Okay, so you are saying like just with random weights. So we should start from like random weights and then use the target and sensitive attribute learning tasks simultaneously.
Right. So you can, I think we actually used like ImageNet or something like that to start for these. And so since the last layer, like you still have to remove the sort of last layer of the CNN anyways, because you have to start from random weights with those since the embedding space is new. But that is a good point. You know, potentially there's some pre-training bias that sort of leaks. For the facial recognition tasks, we don't use pre-training. So that is probably a bit different, but yeah, that's a good point. That I think overall for sort of learning, there's always the potential that sort of pre-training bias leaks into the bias of the ultimate model, for sure.
Right. Last question. So
yeah, no,
it
you're
seems
good.
like you're actually calculating the loss of the whole total loss from parrot, and then you are propagating it back to the CNN backbone itself, right?
Yes.
So your CNN backbone weights are not freezed.
No.
But did you try this experiment, like freeze the CNN backbone network and just use the deep-matrix learning to like equalize the space of the learned features? Or
so freeze the pre-trained backbone is what you're saying?
Or we can like train, like for this particular target task, we know that is like a kind of bias embedding, and then we try to reduce the bias without training the convolution backbone itself.
So basically, you're taking like different steps. So part of the training is just training the sort of target class, and then the next part, I think at some point we had tried doing it non-simultaneously. I believe that might be in the paper, but we found that the simultaneously training worked slightly better. But in the case where maybe you learn, for example, these constant parameters, where you're learning that, I could see how that could be a bit better. Yeah.
Right. Because sometimes you understand, like particularly for medical case studies, sometimes we don't, some like institution don't have enough data to train from scratch. So we already have, imagine like some pre-trained model. So is it possible to use like similar loss formulation to like fine tune the like embedding space with a limited amount of balance or semi-balanced data set, you know?
Yeah, I think that would make sense if, especially what you're saying, like if you first basically learned to decorrelate the two embeddings and then basically mostly did that. And as you said, basically froze it. It seems like that would work. Yeah.
Okay. Thank you.
Any other questions for Natalie?
So Raman, you don't have any question for Natalie? You were fascinated with this paper.
I can't think of any at the moment.
Feel free to reach out to me later also, like I'm happy to answer questions via email or something, so yeah.
We've discussed this paper a few times, so.
Oh, okay, that's good to know. It's always good to
Yeah.
Yeah.
Yeah, Raman, I think one of the best at like the bashing paper is yours probably. He always mention your paper.
Oh, okay. No, that's great. Yeah, no, thanks so much. And yeah, feel free to reach out. Like, I think I can send Nandita my email too to send out, and I'm happy to answer any questions. Yeah.
Awesome. I guess then if nobody else has more questions, we can thank Natalie again for the talk. Thanks, Natalie. And then we'll have the YouTube video up today. And so we'll feel free to check it out in case you miss parts of it. And yeah, as Natalie mentioned, feel free to reach out to us or to her directly. We'll be happy to circulate her email as well. And see you all next week. Thanks for joining us today.
Yeah,
Thank
you
you
so much.